continue from where we left off last time. One thing I wanted to ensure that you understand is the need for these kind of calculations. And I cannot emphasize enough the need for you to understand the relevance of this course. And just to reiterate, I told you that it is about a process engineer who wants to design an equipment, let's say for separation. Separation equipments are known as mass transfer equipment. And if you want to design an equipment which is going to do separation, then you need to know, or you need to calculate what we said is the mass flux. Just as if you want to design a heat transfer equipment, then you need to be able to determine the heat flux theoretically, and use that for the purposes of your calculation. We also said that the flux, whether it's mass flux or heat flux, is a vector quantity that has to be referred to some reference point. So I said it's like if someone standing in Kumasi and say it is 270 kilometers to Kumasi. You are going to ask him where? And then so we say Accra is 270 kilometers from Kumasi. That gives you a reference. And not only that, he also has to say north, south, east, or west. So you have a direction and then you have a magnitude. In the same way, if you want to calculate a mass flux, you need a magnitude, and then you also need a direction. And in the Cartesian coordinate system, which is used as reference, you need three directions, as it were. Instead of one direction, you need three directions. You need the x coordinate, you need the y coordinate, and you need the z coordinate in the rectangular coordinate system to be able to calculate the flux. And so we did a flux balance, if you like, a mass flux balance, and we came up with this equation. Okay, so if we could solve this equation in this entirety, then we don't have a problem. Then we can do all our flux calculations and use it for design purposes. But unfortunately, that is not that's not possible. Okay, so we did an analysis. It came out with the NA del T plus del NAX del X plus del NAY del Y del NAZ del Z is equal to RA. So this is a molar flux balance. Now, the only way we can use this equation is to simplify some terms. And so we set out by saying that one, there's no accumulation. Accumulation is equal to 0. And then we also said the flow is one-dimensional, in which case two terms drop out. And we also said a third condition. We said there's no reaction. By doing that, this term also dropped out. And when we did that, we were left with only this equation. Okay, now we combine it with our defining equation for flux. Okay, let's cancel this. And we'll be using Z. So we're defining the equation for flux NaZ is equal to minus the AB, the CA, the Z, plus X bar A, NA plus NP, where we consider a binary, a mixture of A and B, okay? And this equation that is left, because there's only one dependent equation, it becomes an ordinary differential equation instead of partial, okay? And from here, we choose all kinds of scenario situations that allows us to solve for NaZ, and then we plug it in here, and then we integrate, okay? So for instance, we have one diffusion of A in stagnant B. So that allows us to say B is stagnant, B is 0. We bring Na here, and we still substitute for this NaZ, and then we solve it. And then we get an expression for NaZ in terms of Z. Then we had, let's say this is BA, this is B. We had equimolar, what you call equimolar Cont'd diffusion. In equimolar Cont'd diffusion, we say that Na is equal and opposite to Nb. And what that does, once again, we are able to get rid of this term, and we express NaZ in terms of just this. Then we plug it into this equation, and then we solve it. So we were able to get flux equations for two scenarios. Incidentally, these are simple scenarios, diffusion of one in stagnant other, and equimolar Cont'd diffusion. But in practice, they have practical applications. This diffusion of A in one in stagnant other is applied in gas absorption, and equimolar Cont'd diffusion is also applied in distillation. So you have practical applications. Okay, so we've done that, and we have to bear in mind it all started from this equation. Okay, now going forward, instead of canceling all these terms and solving, we said that, okay, the second set of solutions that we had, we said this is, this goes, this one goes, we have this, but we retain the reaction. And so we have diffusion with a reaction, which meant we considered only these two terms. And that's where we had the reaction being heterogeneous if it happens on the surface, and then we consider the reaction to be homogeneous if it happens within the bulk of the solid. And so if it's on the surface, then we use the reaction as a boundary condition. But if it's within the bulk of the solid, then we solve it as part of the differential equation. Okay, so that is a second set of situation that we looked at. In which case, where we consider two terms, okay, we can, instead of including reaction, we made a brief mention of multidimensional solutions or problems, in which case you have diffusion, which is possible, or a flow which is possible in 2 dimensions. Instead of just one, you have flow in 2 dimensions. And so once again, if we say it's steady state, then this one goes. If we say it's 2-dimensional, we can drop this, and then we'll be left with these two. And then if the reaction is also 0, then you just have to solve these two equations. That results in a different set of problems like the Laplace equation and so on and so forth. The Laplace equation happens after you have substituted for the fluxes with these equations. Okay, instead of for Na, Nc with this, then you introduce concentration in the okay. Now the next if you like, the next major type of problem that we can solve with this equation involved unsteady-state molecular diffusion. As stated here, unsteady-state situations happen at the beginning of the startup of a plant and in batch systems, and these are very important in process control studies. But we will apply it to diffusion in solids. Okay, so if you have diffusion in solids, then we looked at two situations. I said there's infinite, the material expresses in infinite direction, but the diffusion goes in one direction like that, which is finite. So infinite like this, and then you go this way. So you end up with a profile that looks like this. Okay. Now, for the profile to look like this, it means that when you started off, the whole thing was, if you like, it was soaked. It's like trying to dry plywood. If you cut the plywood, the moisture content you assume is uniform throughout. But as you continue to dry it, then it will look like this at some point, like that, and so on. Okay. Because the moisture leaves from the two surfaces, the broad surfaces. Okay. And so we solve that situation is diffusion in an infinite medium, but it's infinite in this direction. And then we saw another situation where you have diffusion in semi-infinite medium, where I said instead of diffusion in this direction, you cut up the infinite direction and the infinite material and diffuse like that. So semi-infinite. And that one results in the error function. And to solve that one, you end up with the error function. The error function is simple to use. Whatever value that you get, you can look up the value of the error function in the table. Now, the diffusion in infinite medium, that one results in a Fourier series, okay, like this. The solution is given in Fourier series. And of course, it's not comfortable to be calculating these things every time you have to solve, a problem in diffusion across an infinite sheet. And so people have used these expressions to plot charts. And it is the charts that we use for solving these kind of problems. And I want to illustrate to you how that is done. Under heat transfer tube, there are similar charts that are used. Okay, example of diffusion across an infinite medium. Okay, in this case, we are using a slab of wood. Okay, like as I said, plywood door or something, and the length of the plywood is like this whiteboard, but we are looking at diffusion not along the length, but diffusion into the slab. So if this is the thickness of the slab. You are looking at diffusion. Okay, the proper setup of this is to assume that the wood is wet. Okay, so you just cut the plywood, or you cut it and it's wet. But you need to go and sell it. So you are not going to leave it in the sun like the dry cocoa to take forever to dry. So you put it in, they put these things in ovens and then they dry quicker. But you need to control the drying as well. Okay, you need to control the drying. That's why they're giving some values. Okay, we want the drying to go from here to here. You need to know that if you don't dry it at the right rate, it affects the properties of the wood. It becomes warped or all kinds of things can happen. Anyway, you are drying from both sides. Okay, so the concentration on the surface in terms of the undefined Y, the CAS is the concentration of moisture on the surface. Okay, the CA naught would be the concentration from the start, which we consider to be uniform. Okay, it's as if the wood was soaked into water and then you take it out. The concentration is uniform. CA naught, and then CA is the concentration at a particular point at a given time after the drying starts. Okay, the concentration at a given time after the drying starts. Now, although there is an analytical expression which is given in terms of Fourier series, but using Fourier series is never an uncomfortable thing to do. And so various people have put the solution in terms of charts. And one of the most popular charts is the Gurney-Lowry chart. If you use the Gurney-Lowry chart, there are 4 parameters that are defined on the graph. There are 4 parameters which are given on the graph. If you are able to calculate 3, then use the 3 to get the 4th one. Okay, and these parameters are A, the unaccomplished concentration change. The unaccomplished concentration change is defined as this. Y, so CAS minus CA was CAS minus CA naught. Okay, where CA naught, I said, is the initial concentration. If it ever falls down to CAS, then of course it means that the driving force for mass transfer will be 0, right? If CAS is equal to CA naught, 0, you can't get any further transfer of material happening. So that's the unaccomplished change. Then we also define the relative position. The relative position is defined as such: N is equal to X over X1, where X1 for the slab is half of the thickness of the slab, because X is equal to 0 is defined to be is defined at the center of the slab. So if you have a slab of a certain thickness, in this case 5, then X1 is half of it, because we are starting from the center. So that would be, in this case, 2.5. And another parameter is the relative time. Okay, these are all dimensional values. Then XD is equal to DAB T times T over X1 squared. Where X1, once again, to remind you, is 2.5. Then we define the relative resistance M. As I said, resistance is 1 over the mass transfer coefficient. Okay, so it means 1 over Kc is the resistance in the gas phase, and 1 over dAb is the resistance in the solid phase. Okay, So that's why I said the numerator resistance, the resistance in the gas phase, because it's 1 over Kc, or maybe I've mixed them up here. The numerator is dAB, represents the resistance in the gas. Is it in the gas phase or the solid phase? Okay. 1 over Kc represents the resistance in the gas phase. Okay? So then the numerator represents the resistance in the solid phase. That's right, good. So dAB is 1 over dAB is the resistance in the solid phase. Okay. So if Kc is large, then just from here, then M is equal to 0. Okay. If Kc is large, then M is equal to 0. If Kc is large, it means that the resistance in the gas phase is negligible. It means that the mass transfer coefficient, when the mass transfer coefficient is high, then there is faster transfer of material between through the gas phase, and therefore the resistance is low. That's what you mean by Kc being large. So in that case, M is equal to 0. But if both are relatively equal, then M is obviously equal to 1. Okay. All right. Now, for the problem, the relative values, are Y, because C is the unaccomplished concentration change. But I said, for these kinds of problems, normally drying, you express in terms of the amount of moisture per the bone dry solid. And that's how humidity charts are also expressed. So we like to express the concentration in terms of the weight percentage instead of concentration of the fluxant. And this is what we do. Just replace the C by W, where the concentrations have been defined in terms of weight. Now, WA is defined as mass of moisture over mass of dry air. Okay. So, therefore, for 20% moisture, which is the CA naught, which is now WA naught, it will be 20 over 100 minus 20. And then, similarly, for 5%, it will be 5 over 100 minus 5. Then we get this. Then 100% is WA, and so on. If you do this calculation, you get 0.294, not 0.94. So that will be changed there. Okay, so when we come here, the relative position is calculated as x1. x1 is 0.25 instead of 0.5, and x is 0. Hence, n is equal to x over x1. Since x is at the center line, x is equal to 0. Therefore, regardless of what x1 is, although it's 2.5, n is equal to 0. The relative time, these values are given. You put the divisivity is given. x1 once again is 2.5 instead of 5, and then m is equal to 1. So we have these values. M is equal to 1, n is equal to 0. We have 0.94 or 0.94 for y, and we have this value for xt. So if you follow what I said, there are 3 properties that we define. If you know 3, then you go to the graph and look for the 4th. Okay. So here, the Gurney-Laurie charts, they look like this. Is a semi-log plot. Semi-log means one axis is logs. In this case, this axis is log, and this one is regular spacing. Okay, so this batch of curves represent a certain m. So this is m1. This batch represents m1, and this represents m2. Okay. Now, within a given m values, m value, you have a set of n's. So, if for M1, you have n is equal to 0, 0.5, 0.5, and so on and so forth. If you go to M1, M1 will also have is n equals 0, 0.5 or 0.25, and so on and so forth. Okay, so if you know your this axis called B is actually your XD. So you pick your M, you pick your N, then you locate it, then you go on this side, you calculate Y. Or if it's Y, you know, you use the Y, you pick your M, you pick your N, then you step down and then you get your XD. In this case, that's what we want to do. Okay. Now, this is the actual graph that you use for a plate or a slab. Okay. And unfortunately, you cannot read these things properly. But because it's logged on this side, you go from 0.01 to 0.001 to 0.1, and then 0.1, and then 1, because it's logged. Okay? So we got y of what? Was it 0.9? Let me go back and check. Y was 0.94. Okay. Oh, sorry. Okay. So, using a Y value of, I think I made a mistake here again. Okay. It was 0.294. Once again, make a note for me. It's not 0.94, it's 0.294. Okay. Okay. So the Y value is 0.294, which after the supposed to be 0.3. So if you go to this graph, this is 0.1, this is 0.2, this is 0.3. Okay. So you go from here, and M is equal to 1. This is M of, I think, 0, M of 0.5, M is equal to 1. So 1, 2, 3, then you go, and then N of 0 is the top curve. Okay, so 1, 2, 3, you go all the way, and here, this is where you find the point. Then you come down, you come down to here somewhere. Okay, now this is 2. This is 1, this is 2. So I read a value of 1.8 for XD. Okay. Can you follow it?
Yes, but
yeah.
If you can take it again.
Pardon?
If you can take it again.
Yeah. So this is the actual graph for a slab. Cylinders also have their graph. In cylinder, the x1 is the radius. Okay, and spheres also have their corresponding graph. Once again, in spheres, the x1, which is from the center line to here, that in cylinders is the radius, and then in spheres is the radius. Okay, so the x1 is, in this case, is half of 5, is 2.5. Okay, so that is even illustrated here. If you get a good graph, you can see. So 4 quantities are apparent in this. Okay, on this left side you have y, and here you have x, big X, either x or x, and inside the graph you have m. These are bunch. This whole bunch is m of 0. This whole bunch is m of 0. This bunch is m of 1. This bunch is m of 2. Okay. Now, within a given m, you have n equals 0 and so on, 0.5 and so on. Okay. So once you calculated those one from the problem, you just come. In this case, we calculated y to be 0.294. And so I'm saying that for ease of, because it's just, academic exercise. So let's call it 3. So this is 0.1, 0.2, 0.3. Then you count. The n equal to 0 represents the line at the top, this one. Okay. For the group M1. For the group M1. If our M was 0, then we'll be using this curve. Okay? So suppose the problem said, instead of the resistances in the two media being the same, suppose the problem said one was negligible. For instance, the resistance in the class was negligible. That would mean the M will be 0. And then we'll be using this. Okay? It depends. You can also say, oh, it's about half. If that is the case, then we will end up using this. And so on and so forth. So now M is equal to 1. So it's this bunch that we use. And N equal to 0 is the one at the top. And when we read it, we got 1.8 as xd. From there, you calculate the time. Okay? And I'm telling you, this one is wrong. For the simple reason that I should have divided 5 by 2. I should have used 2.5. And I ended up using 5. Okay. I just finished it too. Okay. So this is all that I want to do with lecture 5. Okay. Because I promised you that I'll give you an example problem there to demonstrate how we use the gas in solving this problem. These ones we saw this last time, and it's really, if you read it, it's not difficult. All right. So we'll go on to lecture 6.